So the title of today's webinar is Safeguarding Reservoirs, Advanced Flood Routing Solutions. And the agenda for today, I'll first go over some context on the different studies you can do around reservoirs, and then I'll go into explaining why you'd use different levels of complexity and detail in your models. And then I'll go on to give 3 examples of where we've used Flood Modeler 1D to model more complex structures and arrangements such as catchwaters, tumble bays and drop shafts. I've then just got a slide at the end to go through where you might want to use 2D modelling for some of these structures. So the Reservoirs Act of 1930 introduced laws on the safety of reservoirs following the Dolgarrog Dam failure in 1925 that killed 16 people. The Act, in its latest iteration, 1975, makes reservoir owners, operators and managers legally responsible for the safety of their reservoirs. Qualified civil engineers, or QCEs as they're known, are appointed to provide technical oversight and inspect the reservoirs at least once every 10 years and provide recommendations in the interests of safety and maintenance. Example recommendations include the need to demonstrate that the reservoir can safely pass flood events, provide additional drawdown capacity, or perhaps assess the consequence of failure of a dam following reclassification of a reservoir as Category A. The rest of this presentation will look at how we model reservoirs for flood safety. Flood studies are interested in identifying still water freeboard and wave overtopping discharge to determine whether the overflow facilities are suitable for passing the 10,000-year design flood and the PMF safety check flood. Peak outflow is a key output from these flood studies, and these then feed into assessment of overflow performance. A typical reservoir consists of a dam impounding a body of water and an overflow structure allowing flow out of the reservoir into a spillway channel downstream. It can include several other features as shown in the image here, such as bywashes and control structures. However, we often ignore many of the reservoir features, and we can actually undertake a full flood study in Flood Modeler simply using 4 nodes, an inflow, a reservoir unit, an overflow and a downstream boundary. Why do we want to model in such low detail? Well, firstly, there is less of a strain on resources, both in terms of model development and quality checks. The more units in your model, the more room for mistakes. Secondly, there is a danger of modeling for the sake of it. A simple model can often show the worst case scenario, and the client always wants us to be super conservative. The overflow is arguably the most important part of the model, and Flood Modeler gives you the option to choose from 9 different weir units, as well as a flow head control unit, where you can manually input your own rating, which may come from a physical model, for example. When would you deviate from using a weir unit? Well, the weir equation works really well for flow in a channel, but the weir coefficient is fixed throughout the simulation. A dynamic weir coefficient is often more appropriate. In relative terms of depth to width ratio, the influence of the width of the crest becomes less, and it acts more like a sharp-crested weir with a higher coefficient. This is where physical models come in handy in cases where the relationship between flow and head is expected to change significantly at a certain depth above the crest. An important reason to use a physical model is to tell us when the weir is going to drown from the downstream side in cases where the tumble bay has complex conditions. Physical models can provide a more realistic rating relationship that can then be input directly into a Flood Modeler flow head control unit. Typically, the chutes I've been modelling have a gradient of between 1 in 3 and 1 in 5, which cannot be reliably modelled in standard software packages. Physical models are often required also when there is an anticipated problem with the overflow chute that needs understanding. So if you're going to build a physical model anyway to look at the overflow chute, you might as well use it to generate the overflow rating curve too. Physical models are run in steady state, where different fixed continuous flows are run through the physical model to create a rating. So you need to consider there is this problem on reservoirs where the bywash contributes to conditions in the tumble bay, meaning you'd end up with different performances for the overflow weir. You'd have a range of different flow head curves depending on how much flow is coming down the bywash, but the physical model can only provide a single fixed flow time curve. Flood Modeler, on the other hand, is much more adaptable. You can easily change flow distributions or gate settings, but this is not so easy to do with a physical model, making it difficult to integrate into the computational model. Instead, you could use an FM weir unit and treat the physical model data more like a calibration tool. Then, when you do change your model settings, you may be able to better represent different situations. When costing up a job, the key thing to look at is whether we actually need a physical model. If the overflow arrangement conforms to something that can be readily modelled, then there isn't really much point commissioning a physical model. For example, if you've got a broad-crested weir going into a deep tumble bay, Flood Modeller's general weir unit would be appropriate in this instance. Or if a physical model exists on another job for a similar structure, you could apply that rating in your model instead. In cases where the overflow is off from the dam, we don't really care if the overflow literally falls apart, as water wouldn't flow onto the dam or put it at risk of failure. Therefore, physical modelling isn't necessary here, and the findings from your FM model alone would be sufficient for satisfying any safety requirements. The price of a physical model can vary a lot depending on its size, complexity, and the company who are building it, starting from a few £1,000s in my experience. The main concern, however, is often time. If you consider the whole life cycle of a physical modelling job from scoping, commissioning, build, witness test and reporting, it may not be an option if you've only got a few months until your reg date. Often the contractor has several jobs on the go and will need some notice and forward planning to fit the model into their schedule and resource plans. This isn't something that you have to worry about with an FM model, which you could just construct in a matter of minutes or hours, depending on the level of detail you want. A physical model is usually seen as a nice to have, but Flood Modeler can handle a very wide range of overflow arrangements, as I'll demonstrate later on in this webinar. So we use complex reservoir modelling where we have multiple reservoirs in cascade and where we have significant open channel structures, as you can see on the slide. So why model in high detail? Firstly, we need more confidence in the results on dams that are high risk. Where the dam has geotechnical issues, it's more heavily regulated and needs better precision from flood study outputs. We then use the final annotated stage and outflow results as inputs into a reservoir risk toolbox, and the stage in relation to the clay core and the time and depth of head above the core feeds into the geotechnical assessment of dam failure due to seepage. We also need accurate still water levels to feed into wave overtopping calculations, and more realistic assumptions are also needed for design optimization, for example, or even just to determine the level of draw down a reservoir by for safety reasons during construction on the site. The extra investment to do a detailed model becomes less and less relevant if the model is going to be reused for multiple purposes. For example, a detailed cascade model built for a flood study on one reservoir could then be used for assessing flood safety on another reservoir within the cascade. Furthermore, if a client with lots of reservoirs adopts a simple, conservative model for all reservoirs, they're overstating their portfolio risk. It's really not possible to do a high-level conservative assessment on hundreds of reservoirs. There are some interesting features on these complex models that we do have to give attention to. For example, explicit modelling of catchwaters is shown on the screen here, which I'll explain on the next slide. So for some context, the reservoir cascade consists of 6 impounding reservoirs. I've included the upper 4 on the image here. One of the most important of these features is the Reservoir A catchwater. The Reservoir A catchwater comprises of 1.8 kilometres of open channel and 2 culverts, and this all intercepts flows from reservoirs B, C and D catchments and diverts them to Reservoir A. The catchwater exists because Reservoir A sits much higher than the other reservoirs, so water can be easily routed out from here to neighbouring systems via the pipe network. Ground levels on the right bank, i.e. the west side of the catchwater channel, drop away, and any overtopping flows would bypass Reservoir A and overspill into reservoirs B, C, and D. The distribution of spillages into these three reservoirs does depend on what point along the catchwater channel a blockage may occur. The catchwater open channel was represented in this case with cross-sections and interpolates with lateral spill units on the right bank. The laterals are then connected to musculum units to represent the movement of spillages to each reservoir. Musculum units determine the flood peak attenuation and the lag time of a flood wave as it passes through a routing reach. The catchments are all very small, and so the timing of the spillages would make quite a difference to peak flows within each reservoir. Therefore, modelling the travel time of the spillages was important, which is what musculum units are good for. And another reason why musculum units were chosen in place of, say, river cross sections is because the slopes were very steep and because we weren't particularly interested in water levels along these flow routes. Now I'll move on from modelling catchwaters to modelling tumble bays. So this next case study demonstrates the application of FM for modelling a common but nonetheless complicated overflow arrangement. Let's start by building the model from downstream to upstream. There are a number of things going on here, meaning we cannot assume that a freely discharging weir equation is appropriate. Once the chute goes under the bridge, it suddenly goes very steep down some steps. We can't effectively model this steep step section in 1D, and so we need to stop the model extent here and apply a boundary assumption. But what downstream boundary is appropriate? So a location was identified on the chute where the channel suddenly goes really steep. At some point, flows will move from subcritical to supercritical at this sudden change in gradient, and so we can assume we go through the critical depth around here. Therefore, the model was set up with an FM critical depth boundary downstream of some surveyed cross-sections of the spillway, which you can see here. Results actually showed that the supercritical flow is achieved within the tumble bay because it's hydraulically steep, meaning there isn't actually any suitable location to apply a critical depth boundary. Thus, a normal depth boundary was chosen instead, which assumes water level is parallel to the bed slope. Supercritical flows tend towards normal depth based on the gradient, and so the normal depth is the best available option we could use here. We put the steep gradient of the stepped chute as the slope within the normal depth boundary and assume that the boundary was sufficiently removed from the weir itself. Regardless, we couldn't extend the model any further downstream as any 1D modelling software would struggle with such a steep gradient. This isn't a perfect representation, but it's the best we could come up with from the tools available. Then the next thing to consider in this model is the impact of this bridge you can see on screen. If the bridge is undersized, it could back up and form a control. Initial model results showed that there was sufficient freeboard to the bridge deck even with conservative assumptions. Given the bridge had no abutments constricting flow and was well above water level, it no longer needed representing in the model, so was removed. We then wanted to explicitly model the tumble bay to know whether the weir would drown. The tumble bay was represented with an upstream and downstream cross-section, and as you can see on screen, flows over the weir have to take a sharp turn to the left, then contract within the narrow spillway channel. And the limited capacity of the channel could form a control downstream of the weir if it becomes fully drowned. An FM head loss unit with a high coefficient was therefore added to the model to account for the 90-degree turn in the tumble bay. There's also a bywash that discharges into the tumble bay, which could push up levels in the tumble bay. The bywash channel was modelled explicitly and dynamically linked to the reservoir and connected to the tumble bay, as you can see here. This was the best model we could produce with the tools available, but you need to think it does fail to capture the impact of super elevation and turbulence. Now I'll move on to a less common arrangement that you may have to model, which is a drop shaft. So some reservoirs have drop shaft spillways where the weir drops vertically down a shaft and then flows horizontally via a culvert through the dam before discharging downstream. Initially, the system works like a weir around the circumference of the entrance, but as water gets higher and flow rates increase, water level hits the top of the culvert and there is friction loss over the full length of the culvert. From this point, water level will back up from the culvert and rise higher and higher up the drop shaft until it drowns the weir. From this point, it acts as a pipe full system and head increases massively with any small flow increase. Before you start building the model, the first step is to determine whether the drop shaft actually needs representing. In some cases, the weir may not become drowned even in a PMF event, in which case you can represent it with a weir freely discharging. You can determine this just with small models or calculations in a spreadsheet. You'd like to think that the system is sized to take its design flows, but some assets are really, really old, whereas the design standards have increased considerably since they were built, so the drop shaft may need explicitly representing in the model. So on screen here is an example of how you could explicitly represent the reservoir drop shaft overflow in Flood Modeler. I would first set up a weir unit to represent the crest of the overflow around the perimeter of the shaft. Then I'd connect this to a reservoir unit representing the vertical drop shaft, as you can't use a culvert in the vertical. At the transition between the vertical drop and the horizontal flow, I'd use an FM general loss unit, picking up velocity from the downstream unit. I'd then represent the horizontal flow through the embankment using a standard culvert schematization as shown. You may also want to add additional minor head losses through the system, whether there may be an interruption to flow, such as, say, bends, valves, or transitions between culverts of varying sizes. The importance of minor head losses will vary depending on your arrangement. For example, if your horizontal pipe is very long, then the minor head losses are potentially not as important as the friction loss. The schematization of the drop shaft using a reservoir unit can potentially overestimate performance because it ignores friction losses within the shaft. An alternative method is to replace the reservoir unit representing the vertical with a second culvert, which will account for energy losses due to friction. So I'm going to flash that next schematic up on screen now. So within the model, the culvert should be flat in its gradient in FM and its length set to the vertical height of the shaft, assuming that the full height of the shaft is full of water. Flood Modeler will output the hydraulic grade line, which you can plot and visualize using the results window. A bend loss unit is also added to represent the losses associated with flow going from vertical to horizontal. Something to note with this schematic is that the culvert option gives head loss for the entire shaft, meaning we are overestimating losses if water level only comes part way up the shaft. An iterative process of changing the length of the vertical pipe is therefore needed so that the length of the vertical culvert matches the depth of water within the shaft. The reservoir option is preferential when modelling low flows, as it can deal with the shaft being dry, whereas you would always need flow through the system if using the culvert approach. You can see here I've also replaced the weir unit with an entry loss unit. You do this if your weir is going to be drowned out. If I flick between the two slides now, you can see I've also made changes at the downstream end. Let me just flick between them now for you to see. So in this first schematic, I've used an outlet unit connecting the culvert with the downstream watercourse. This setup is applicable if the culvert is expected to be drowned and impacted by downstream water levels. Now, if we flip back onto the second schematic, you can see I've terminated the model right at the downstream end of the structure. This is a good option if the outlet is followed by a drop and is falling off into space and isn't going to drown. The best way to transition from high ground to low ground is with a flood modeler spill unit representing the bottom half of the culvert cross section, which is then connected to a freely discharging head time unit. There are cases where you may want to represent your reservoir structures in FM2D, for example, to obtain velocity estimates of flows overtopping the dam. Many reservoirs are designed with a wide section of the embankment lowered to act as an overflow, as shown on the slide here. I don't know if you can see, but this section here is a bit lower than the ground here and here. The overflow is designed to come online in high magnitude storm events and send flows over the dam crest and down the downstream face. Flood Modeler 2D can be used to understand velocities over the embankment to inform design of surface protection for the downstream face of the dam, such as grass growing through revetment blocks, for example. All you'd really need in your 2D domain is your LiDAR or survey data to create the model DTM for the embankment and overflow, and then link this dynamically with your normal 1D model of the reservoir. A second use of FM2D for solution design at reservoirs is when there is water spilling out of the chute onto the dam and threatening its integrity that way. In this example, we could use FM2D to understand flow direction and mechanisms to help inform design of bunds to route the water back into channel. We do have a goal to integrate 2D domains into reservoir flood routing models on more sites, as we know Flood Modeler 2D has this capability. So to summarize, I've got 4 key points that I want you to take away from this. The first one, don't just model for the sake of it. How much complexity do you truly need in your model? Second, physical model data can be incorporated into your FM model to better represent your reservoir overflow, but do be aware of its limitations. Third, FM can be used to represent a wide range of reservoir structures. The Victorians created so many weird structures, and we're constantly having to think how on earth we can model these. Flood Modeler is being completely rebuilt for version 8, which is due to be released later in the year. This will include enhanced, fully integrated units, such as the revamping of the weir unit. And I'm hoping these newly developed structure units will help deal with some of these non-standard reservoir structures. And then my final takeaway point from this webinar is that there are multiple ways to schematize the same thing, but just think carefully about what conditions you expect to see and use this to inform your decision.